part 2. For the part 2, we can describe the graph model, which is the first subpart is a query implementation. We need to design a graph-based data model with the following the structures. 3 types of the nodes we need to create, which are users, trip, and the stations, and the 3 types of the edges: performant, starts at, and ends at. So based on this schema, we need to provide implementation of the following queries. First query is a given user, find all stations reachable through their trips, and the second query is to find the 3 most important stations based on the number of the incoming and outgoing trips. We need to use our data sets, users, trips, and events. So we can see our results. This is our scripts path. We can see part 2 folder includes our setup Neo4j and queries for the Neo4j Python files. We can see in the part of the code is in here. What happens in here is that the first locate in the user node users their ID because of the indexing, of course. The main difference between the other database relational and the document database and the graph database is the that field, that function, of course, and Neo4j can find this node quickly enough. So from that user, we traverse one hop to all trips. They perform it, and from each trip we move another hop at all stations using both start at and end at relationships. So that edge types of that cases also we use the same logic of that case, of course. And then main overall summary was the Neo4j performs well because the first query it used index-based lookup for the user node and then follows direct relationships without any scanning the table. As we remember, the PostgreSQL with the join query, MongoDB with the lookup query, every time it needs to scan the database tables. For that second query, for the second query, we can see it simply traverses edges between trips and the stations, which grows linearly with the number of the trips but remains efficient because GraphDB uses pointer-based storage instead of the join operations. And graph-based DBs are strongest for recommendation logics, complex relations, but it is not good at aggregation, especially ACID-based logic projects. This is our discussion and our comparison and summarization. So the next part is Spark-based implementations. After that, created that tables and that columns, we need to provide Spark-based implementation of that following queries, which is first query find the 3 most important stations based on the page rank value for the stations, and for the computation of the page rank, we can use graph frames libraries. And the second query, we need to compute connected components of the station subgraph. For the computation of the connected components, we can use implementation of the graph frames libraries. In our comparison, we can use as the same data sets, of course. What we did, our script was Spark graph frames.py, and the vertices, which is the stations, its name, ID, and the city. And we used this part. We implement each graph analytics with the Spark and the graph frames. Firstly, we built graph structure, of course, in here. We define the stations where has ID, name and city. Then we create edges from the trips where each trip connects and start station and end station, of course. After preparing vertices and edges, we construct graph frames, which allows us to run graph algorithms on top of the Spark. Now, first task, computing page rank. We can see in the parts of the code in here, and it finds the 3 most stations. The result shows that highest named stations, cities like that. For example, in here, our result, we can see the Florence and the Rome, which is the top stations based on our result. And that result, we can see all the 50 stations belong to single connect component. It means the entire network is fully connected. There are no any isolated stations, and every station can be reached through some sequence of the trips. So, and finally, in terms of the results, we can see PageRank is a faster, taking around 3.8 seconds. 3.8 seconds. This is a PageRank station based on the top 3 stations, and fully connected components take around 9.9 seconds. The reason is across graph and uses checkpoints, which introduces additional disk input-output overhead. This is our discussion based on our performance. So the last point is partition and replication plan. We need to assume that trips of the collection is partitioned either by user or by start station. For each choice, we need to describe how it would impact on the execution of the queries, both part 1 and part 2, especially focusing on which queries would benefit or negatively affected by the partitioning strategy. State which partitioning strategy would we adopt and why. So what we did in here for the partitioning case, so in this part we implemented the graph analytics using Spark and the graph frames, and of course in the system we need to consider 2 partitioning strategies for the trip collection by user ID and by start station ID. First option, so strategy A. This approach, all trips belonging to the same user stored in the same partition. This is very efficient for the user-centric queries. Like, for example, on the query 1, if you remember, user is a reachable stations. It becomes fast because all users trips are local. And query 2, which is to find trip count and average duration per the user, it is also efficient because aggregation is done within a single partition. But station-based analytics like the query 3 becomes expensive for that case, because trips for same station are spread across all user partitions, and this forces full scatter-gathered operation. Like, for example, we have 2 shards for example 1 and shard 2. In here, user 1, for example, user 1's partitioned in here, for example, the trip 1, station 2, for example. And for the second chart also includes like these operations, for example, trip 2, 3, station 1, station 3, for example. In that case, station 1 repeated 2 times for each chart. It means while the filtering, it needs to scan both of the charts. This is called scatter-gathered. So for the strategy B, like the second option, here all trips starting from the same stations are stored together. This benefits station-based queries like query 3. We can take as an example, like, since counts per station are local, but if we want to filter them like the user-based, it becomes slower because single user strip are distributed across multiple partitions. It requires cross-shared operations. This is a main difference between the first strategy and the second strategy. And our decision is we recommended the user ID partitioning type, because here all trips we can see starting from the same stations, like all of the same stations are stored together. This benefits station-based queries like query 3. We can take as an example, since counts per station are local, but if we want to filter them user-based, it becomes slower. So our final decision about the partitioning, we choose partition by user ID because the system is mainly user-centric. Most important queries like query 1 and query 2 are also user-based and benefit from data locally. So last part is replication. Assume the data about trips and replicate it according to the single leader asynchronous replication mechanism with the one primary replica and two secondary replicas. We need to describe events on the implementation queries, both part 1 and part 2. What could happen if a query is served by a secondary replica, focusing in particular on whether results and queries could be inconsistent. So what we did in this case, in this setup, write operations, it means write operations go to the primary firstly, and then it propagated to secondaries. It means the other secondary replicas reads from the first primary replication. If query executed on the secondary replica, result might be slightly stale. Stale means it shows the old data due to the replication lag. So impact on the queries, query 1, for example, user strips and stations may miss the latest strip. It means slightly outdated user view. And the query 2, user stations counts and the averages may be temporarily incorrect. Like its risk points are trip count and the average duration may be undercount if the secondary has not yet received the latest trips. This is like the monotonic read we can see. And for the third query, station analytics, it is binary stateless is acceptable. This is not too much big problem, but the risk points are the same as a query 2. Counts may be slightly stale. For the especially analytics reports purposes, minor lag is acceptable. That's why. So, and for the query 4, trips with the error events, the risk are more critical. Missing recent error events can lead to incorrect monitoring results. And it means error detection queries should always be routed the primary replica. This is a little bigger risk. And for Neo4j query 1, the query 2, same considerations apply. New trips and their edges may not be replicated to the secondaries. That because graph traversal on the stale data returns incomplete path. Conclusion is we can use primary for the real time for safety critical queries, and for the we can use the secondary for analytical queries. Recommendation is real time and safety critical queries to the primary replica, and we can use for query 2, 3 and to the secondaries distributed read load, and for that case smaller lag is acceptable. This is our comparison and the performance results table and the graph we can see, and our main conclusion for each part and full conclusion of the project. So project shows multimodal data system design, where different DBs are used depending on the workload. PostgreSQL performs best for the structured, join heavy queries like the user analytics. MongoDB is highly efficient for the embedding event queries and flexible schema evolution. Neo4j is the best choice for the graph traversal and relationships heavy problems like the station reachability. And the Spark is suitable for distributed analytics and large-scale graph processing. The main idea is there is no any single best DB, but each system is optimized for specific type of the workload.